Last video we ended by defining what it means for a linear map from v to the n to r to be multilinear. And just to remind you what that is, so the main example is, so the vector space v for us is going to be r to the m, well, r to the n for us, and then v to the n is going to basically represent n by n matrices, because we're thinking of r to the n, elements of r to the n, as being our rows, and so v to the n is elements of v to the n is going to be n rows, just put into like an n tuple as right here. So that's the notation even reflects that, like row sub 1 as a vector. We're thinking of this as being the first row, and the second row, third row, up to the nth row. So v to the n is really going to be like the set of matrices for us. And so for a map to be multilinear, it needs to satisfy a sort of additive property. Right, linear maps say that f of v plus w is equal to f of v plus f of w. Multilinear says that that holds sort of in one coordinate, where you're keeping all the other coordinates the same. So the other property that went along with it was the property that, so like linear maps say that f of k times vector is equal to k times f of vector, but multilinear says that that same thing should be true only in one of the components, and all of the other components stay fixed. And this is for all rho I, for all v, for all w in your vector space v, which we're thinking of as rows, and for all scalars k and r. So this is our definition of multilinear. And the main example that you want to have in your mind for this is determinants. Determinants are multilinear functions. They satisfy these two properties. So the idea is to just show that the idea for why this is true, I mean, is to show that if the determinant function from n by n matrices to R satisfies the four determinant properties, and those are the properties that were just included in the definition of a determinant. A determinant is a function that satisfies the four properties that if you add a scalar multiple of one row to another row, that doesn't change the determinant. If you multiply a row by k, that multiplies the determinant by k, or the new determinant is k times the determinant of the old determinant. That's what I mean by that. That's what I meant to say. And the third one was that if I swap rows, then the determinant changes sign, and if I have the determinant of the identity matrix is equal to 1. Those are the four determinant properties, and the idea for this proof is you have to say that if we have those four properties to work with, then the determinant function satisfies the properties 1 and 2 in our definition of a multilinear function. So we have to show that it satisfies this property and this property. And property 2 is a property that we already have, because this is saying that so think of this as being our original matrix, and if I multiply some row by k, then the determinant of this matrix is k times the determinant of the previous matrix. Right, so f is like the determinant function. So k times determinant of matrix is equal to the determinant of the new matrix that you get by multiplying that row by k. So So property 2 is a restatement of the property that says that if A row reduces to B by taking k times row I, then the determinant of B is equal to k times the determinant of A. And then property 1, I'm not going to go through the proof of that. It is in the book, and I would recommend you read that if you are interested, but I want to keep moving. By the way, for some reason, my iPad keeps having issues with scrolling, so I'm trying to scroll on my iPad right now, but it won't work. But if I back out and then come back in, then it starts scrolling again for some reason. So I'm probably going to do that a lot during this video. I apologize for that. Okay, cool. So let's do an example. I sort of hinted at an example last time, but this one I want to go a little bit further with it and start showing you how to actually find the permutation expansion for a matrix. And it's just so this is just going to be a way to split up this the determinant of a matrix using the multilinearity properties, specifically property 1 we're going to use repeatedly, and then we're going to use property 2 at the end to calculate the determinants of the smaller matrices that we're going to split this up into. And so let's just do it. So the first thing we want to do is split up. We can split up row 1. So this is like row 1 and row 2, right? And we can split up row 1 into 2, 0 plus 0, 1. And therefore, the determinant of this matrix is equal to the determinant of, so I split the first row up into those smaller components, and then I keep all of the other rows the same, and there's only one other row here, so it's not much work to do with that. Let me erase this for more space. And that's what we do for our first step. And then for our second step, let me make these different colors. For our second step, we'll split the blue matrix into 2 smaller matrices by splitting the second row into the rows 4, 0 and 0, 3. And then we'll keep the other matrix, the other row the same. And then for the black matrix, we will do the same thing. We'll split it up into 2 rows and keep the first row the same. And so this is what we get. All right, cool. So this is about as simple as you can break this up. You could go a little further with property 2 by pulling out all of the scalars from each row. And so, all right, before I do that, let me just say that there are 4 determinants here, and a couple of them we already know are 0 without having to do any sort of calculations. Why do we know that? Well, we already know that the determinant of a singular matrix must always be 0. So the determinant of this matrix here is 0 because in particular we can say that this matrix is singular because its rank is 1 in this case. So I have a row right here and a row right here where this row is linearly dependent on the row before it. Therefore, the row rank is equal to 1, so this is a singular matrix. And then also over here, I have 2 entries in the first column, and I have, maybe a better way to think of this is that I have a column of zeros here. Because I have a column of zeros, the column space has to have, I'm trying to say, yeah, the column space should have dimension less than the size of the matrix. So this determinant 0, this determinant is 0, and so we could just ignore them. All right, so let's ignore those ones and then just pull out the scalars from the other matrices. I'm going to treat the entry 1 as like still being a scalar and pull it out because we're going to do that with like all entries later on. I'm just trying to be like general here. So this is what we get here. This matrix right here is our identity matrix. So that determinant is positive 1. And this matrix right here, this is an example of a permutation matrix. If you recall, we talked about permutation matrices before. Permutation matrices are obtained by taking the identity matrix and doing a bunch of row swaps to the identity matrix. So in particular, permutation matrices are always non-singular matrices. They're always row equivalent to the identity via only row swaps. And so the determinant of a permutation matrix is going to be always plus or minus 1 because of that. And to determine whether it's plus or minus 1, you just count the number of permutations, count the number of row swaps, rather, to take it to the identity matrix. And here, of course, we only have to swap rows 1 and 2 to get to the identity matrix, so that determinant is negative 1. And so this determinant here is 6 minus 4, which is 2. And so this is the permutation expansion for, well, specifically this right here is the permutation expansion for the matrix 2, 1, 4, 3. You could argue that this is the permutation expansion, but like they're equal. Like this determinant is equal to positive 1 and this determinant is equal to negative 1. So whatever floats your boat with that. Really, the permutation expansion is just the way that we can explicitly calculate the determinant of our matrix using only the elements or the entries of our matrix. Right, these four entries all show up in this calculation, and the only other things that show up is the plus and minus ones. And well, so let's do a bigger example so that we can sort of solidify this example a little bit more. Sorry, this circle should not be here. Okay, cool. So let's do a 3 by 3 matrix. So we're going to split this into a sum of many simpler determinants. And notice that this 0 right here, I put a box around it. If I go back to the previous example real quick, at the end right here, I factored out all of those entries from these matrices. If like one of those entries was a 0, you can still factor out a 0. Right, you would have 0 times the determinant of something where you now change the determinant of this thing to be positive or negative. But because you're multiplying by 0, the determinant's still 0, so that's still technically allowed. You can do that. And putting a box around the 0 is just going to help us keep track of like which zeros are going to be coming from the original entries from the matrix, and which zeros are coming from splitting it up into smaller matrices. Okay, so let's do this. Let's first split this matrix along the first row. And so if I do that, my row will split into 2, 0, 0, 1, 0, 1, 0, and 0, 0, negative 1. And all of the other rows will stay the same. And already maybe you can see why boxing that 0 is going to be going to make our lives a little bit easier in this calculation. Okay, let me make this a different color. That'll be blue. That'll be, I don't know, red. And so now I'm going to split my blue matrix along row 2. So row 2 will be split into 4, 0, 0, into 0, 3, 0, 2, and 5, and then 0, 0, and then boxed 0 coming from the original thing. Okay, and then I'll do the same thing for row 2 of the second matrix, but really I don't want to go through all of that. And then I would do the same thing for the third matrix, our black matrix. So you'd have something in each of these matrices. But we're still not done yet, because our end goal is to end up with a matrix that is as simple as possible. So up here in this example, we wanted to end up with matrices where we can no longer split up the rows and columns anymore, and we could just factor things out and be left with either permutation matrices or things where the determinant is clearly 0 because it's singular. So we're not there yet. We would want to split each of these matrices along the third row. And so for each of these 9 matrices, we would split it up into 3 more matrices. And so we would get 27 total matrices. And I am not going to write all of those, but I do want to write like a couple just to like tell you like what types of matrices I'm getting there. By the way, in general, so like for an n by n matrix, it would split in general into n to the n simpler determinants. Like in this case, we had 3 by 3 matrices splits into 3 cubed, which is 27 simpler determinants. Okay. Cool. So let's see. Let me copy and paste this because this is actually take 2 because I kept misstating what I thought certain entries were. So I'm going to bring this along with us. All right. So this is going to break into 27 smaller matrices, and some of the ones that you'll get will look like this, where like maybe you get all the entries in like one row, or maybe you get like 2, 4, 5, or 4, 0, 1. And I'm not writing this in like any sort of organized way right now. And then maybe I get like 2, 1, 5, something like that. And that'll be like the last one I write for these ones. Okay. What do these all have in common? Well, all of them have either a row or a column of zeros. And this is because each matrix has only 3 entries in it. It's a 3 by 3 matrix with only 3 entries. If one column has at least 2 entries in it, 2 non-zero entries, since you have only 3 entries to work with, and one column is hogging 2 of the entries, then at least one of the other columns is going to be an entire column of zeros. Or vice versa, maybe one row has 2 non-zero entries, and that would leave another row to have a whole row of zeros. And maybe let me actually change this one to do I want to do that to now I'm going to put that in the next line. Okay. Okay, so these all have determinant equal to 0. But what are some of the ones that we could have that have non-zero determinant? Well, maybe we could have 2, 3, 5. This is just this one's clearly row equivalent to the identity, right? We're just multiplying the rows by 2, 3, or 5. We could have 2, 0, 1. We could have 1, 4, 5. We could have all sorts of things. But the upshot is all of these guys are going to have at least one entry in each row and at least one entry in each column. And because of that, so that property ends up being equivalent to the definition of being a permutation matrix. So if I were to ask which matrices in our expansion have possibly have determinant non-zero, the answer would be the matrices with exactly one entry in each row and each column, which coincides with the permutation matrices. And so I can, instead of writing all of the possible matrices that you would get in this like 27 term long expansion here, I'm going to throw out all of the ones that have like 2 entries in one column or something like that, and I'm going to be left with only the ones that have 1 entry in each row and each column. Okay, so let's do that. Let's just split this matrix up into smaller matrices and see how many we get. So let's say that in the first row and first column we have the entry 2, and then that makes all of the other entries in that row and column equal to 0. And then I have 2 more entries to work with coming from this like smaller matrix, and then maybe I pick that one to be a 3, and then the other ones will be a 0, and then I'm stuck with that one being a 5. Okay. There are more choices I could have made if I picked a 2 for the first entry. I could have made this one a 1, which would make this one to be a 0. And that one's also perfectly legitimate. This has an entry in each row and column. Even though this boxed 0, we're treating that as an entry. This matrix is going to have determinant 0, but I want to still account for this one despite that. We'll maybe see why later. It's gonna affect our formula at the end, but okay. So that's all the ones that have a 2 for the first entry. So for now, our 1, 1 entry will be 0. And then maybe we'll have a 1 for the first row, which means that column 2, everything below that 1 is going to be 0. And then I could have either a 4 here, which would force that to be a 5. Or I could have a 2 here, which would force those to be 0s. And then I would have the boxed 0 right there. Or for my first row, I could have picked a -1 to be in the top right corner. And I could either pick 4, 1 for those entries, or I could pick 2, 3 for those entries. And yeah, that's it. So I organize this according to like where is my first which entry is going to be non-zero from the first row, and then I only have so many choices for the next couple things, right? I picked where in the first row my non-zero entry would be. That chopped out the rest of those choices, and then I had 2 more choices for like what my first entry, for what my non-zero entry in the second row would be, and then I had only 1 choice for my last entry. Okay. So in general, what I'm describing there, so like if this were an n by n matrix, So for n by n matrices, there will be n times n minus 1 times n minus 2 times dot 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 times 3 times 2 times 1 choices to be made, and therefore there will be that many matrices. And some of you might recognize this. This is the factorial, so this is n factorial matrices. And that holds in this case. Here I had 3 times 2 times 1 choices, so there are 6 total matrices here. Okay. And the point of that is just that tells you how many matrices there should be in this calculation so that you know that you're not missing anything. Okay, great. From here, I want to factor out all of the entries here, including the boxed 0. I'm going to still factor out that boxed 0. You'll see what happens in a second there. And then I'm going to be left with permutation matrices, and then to calculate the determinant of the permutation matrices, I'll just count how many row swaps I need to do to get to the identity. Okay, so let's maybe get rid of this so that I can just see a little bit better. Okay, so this is equal to, I'm going to factor out a 2, a 3, and a 5 from the rows of the first matrix. I'm left with the identity matrix. Factor out a 2, a boxed 0, and a 1 from this matrix here. And again, I'm allowed to do that because this 0 makes this entire term equal to 0, and this matrix had a row of zeros technically, so its determinant is 0, and this whole term is equal to 0, so I'm still allowed to do this. Okay, second row, I'm going to factor out the 1, the 4, and the 5. Be left with 1, 1, 0, 0, 0, 0, 1. This one will have 1, a box 0, and a 2. This one I'll have a 0, 0, 1. Should factor stuff out first. Negative 1 times 4 times 1 times 0, 0, 1, 1, 0, 0, 0, 1, 0, plus negative 1 times 3 times 2 times this matrix. Okay. Am I happy with that? This is the right matrix. I just want to make sure I have the right matrix. 2, 1, negative 1, 4, 3, box 0, 2, 1, 5. Cool. Okay, everything looks good here. Okay, I know my answer should be 12 at the end, and I made an error at the end of the this example in the last video and had to start over again, so I want to make sure that I get it right this time. All right, so this first term is going to be a 30 times positive 1. Second one's going to be a 0 times negative 1, because I only have to do one row swap. I swap rows 2 and 3, and that'll take me to the identity. And our fourth property of determinants is that the identity matrix has determinant 1. This term will be 20 times, I could swap rows 1 and 2. That'll get me to the identity matrix. This one will be 0 times, so this whole term will be 0, so technically you wouldn't really need to worry about this one here, but you will have to worry about it in your own examples, and this example is a little harder anyway. Should this be a +1 or a -1? So you might be thinking that it should be a -1 because I have to do some row swaps to get to the identity, but you have to count whether that number is even or odd. But anyway, so let's do it. So if I swap rows 1 and 2, what would my next matrix be? that would put this one here and this one here. So I would actually get this matrix right here. Okay, so I did one row swap and I obtained this matrix. And now I could swap rows 1 and 3, and that would take me to the identity matrix. So because I multiplied by -1 twice, I did 2 row swaps. My determinant for this matrix is +1 and not negative. Okay. All right, what about for this guy? So this is -4 times, it's going to be positive or -1. All right, let's swap rows 1 and 2. So 1 would be here, 1 would be here, and then I would have to swap rows 2 and 3. So in other words, if I swap rows 1 and 2, that would take me to this new matrix here, because I'd have a 1 right here and a 1 right here by swapping rows 1 and 2. And then I would swap rows 2 and 3, and that would take me to the identity matrix. So I did 2 row swaps. So that determinant's +1. And then -6 times, and then here I can swap rows 1 and 3, and that'll take me to the identity. So +6, or +1 times -6. All right, this whole thing turns out to 30 minus 20 minus 4. Oh, this would be, sorry, this should be, I only did 1 row swap, that should be negative. Almost messed it up again. Okay, great. +6. All right, so I get 30 minus 20 minus 4 plus 6. This is 10, this is 2, that makes 12. So our determinant is 12 by using the permutation expansion. One thing to keep in mind here, this permutation expansion right here, so all of the terms in this expansion are, let me back out so I can scroll again. All of the terms in this expansion are terms from our original matrix, and further, so we have these permutation matrices here, and the determinant of the permutation matrix is, it's maybe not clear that that the determinant of a permutation matrix is well defined, and in fact, like in the following section, that entire section is basically, well, a large chunk of that section is devoted to talking about why the determinant of permutation matrices is well defined. But it basically amounts to you always have to do either an even or an odd number of row swaps to take a permutation matrix to the identity matrix. And so because the number of row swaps is always even or it's always odd depending on your starting permutation matrix, then whether that determinant is +1 or -1 is a well-defined thing. And so this expansion here that depends only on the terms of the entries of your original matrix and the permutation matrices that go along with it, because this determinant only depends on those things which come from your original matrix, then this is a well-defined thing, and this tells us, hey, this actually is a well-defined function, and so determinants exist and they are well-defined, and that's all because permutation expansions exist. Okay, so I want you to try these next 2 problems. I think the video is probably getting a bit long here, so I am just gonna let you try this, and I have solutions written up in the notes for you to try, but for you to look at and check, I mean. So yeah, give these 2 a shot. I think that you'll really learn this a lot better just by doing a lot of examples here.